Hello and welcome to another video. So today we're going to start a new topic, and the topic is on mathematical induction, but this topic will also include some introduction into other topics such as relations and functions, and also recursive algorithms. So again, as I've been saying all along, if you've never heard of these topics, we're going to define what they are, we're going to start from the bottom, and we're going to kind of work our way up. Now, let's start with mathematical induction. So, mathematical induction is the majority of this section, the majority of this topic. And the first thing we're going to get into is this principle called the well ordering principle. So, this is the basis for mathematical induction. Mathematical induction is a way of completing proofs. So, if you recall, the types of proofs that we've seen already in this course involve showing validity, right? So, we started with the premise, right? So, we started with whatever, however many premises we have, and then using logic, using inference, using mathematics, we argue that a conclusion must always be false. Sorry, it must always be true and cannot be false. Uh, the general form, therefore, that the types of proofs that we've been making is in this form: P implies Q. And this is the strategy that we would use for P implies Q. We assume the premise and then show the conclusion. Now, in this section, instead, what we want to prove is forms that look slightly different and do not necessarily have the implies that's in there. So forms that look like this: for all n p of n in some kind of universe. We'll say for all n that is in, for example, z plus. Now, the first thing I want you to notice is that there's no place in this expression that has the implies, right? So we can't really use the assume, premise, show, conclusion strategy, but there is another strategy that we can use. The second thing I want you to see is that there is a limitation to the universe that we're working with. So the universe that we're working with here is z plus a positive integers, meaning that there is some sort of beginning, the number one, and then it goes onwards. Even though that this is an infinite set, the universe is infinite, there is a starting point. And those 2 points are very important moving forward in mathematical induction. So let's take a look at some properties of integers. So first, let's start with a motivation. All right, so if I were to ask you, what is the sum of the first n odd numbers? Okay, what is the sum of the first n odd numbers? So maybe I should be a little bit more specific for first n positive odd numbers. So so the first odd number would be 1, second odd number would be 3, and then 5, and then 7, and so on. So if we were to make kind of a small chart out of this, we can say n goes here, and then what is the sum of the first n positive odds, right? So what is the sum of the first n positive odds? So if I said, what is the first one positive odd numbers? Well, it would just be 1. If I give you two odd numbers, then the answer would be 1 plus 3. So the sum of the first two odd numbers would be 4. The sum of the first three odd numbers would be 1 plus 3 plus 5, which is 9. And then if I give you four odd numbers, 1 plus 3 plus 5 plus 7, which is going to give you 16. All right, so now we can keep going like this. And what if we get down to n? So what would be a good guess for the sum of the first n positive odd numbers? Now, you can just stare at it and see if you see a relationship between the right-hand side column and the left-hand side column. And I think the pattern that is coming out is n squared. Now, is this a proof? Is it a proof that every single n is going to give me n squared when I sum the first n positive numbers or positive odd numbers? And the answer is no, right? So this is by no means a proof because I've only shown you 4 cases. What if it breaks down after 5 cases or 6 cases or even 100 cases? So what we need to do is come up with a mechanism to be able to prove this. Now, understand that this is quite difficult because we're talking about an infinite number of n's, right? We're talking about infinite number of n's. But as I said in the introduction, there is a nice structure to this because there is a smallest point, the smallest point being 1. There's no n that's going to be less than 1. Right, so we can use that to our advantage, and I'll talk about how that goes in 1 second. But for now, let me put down a guess. Okay, this guess is something that we're going to prove eventually. But our guess is that when we sum the first n odd numbers, so when I sum I equals 1 all the way up to n, now please recall the form of the odd number, right? The odd number is in the form 2i plus 1 or 2i minus 1, where I is an integer. Right, so here I'm going to sum up the i's from 1 up to n of 2i minus 1. Now, please just make sure that you realize that this gives you the first n positive odd numbers. So, for example, if I plug 1 into the I get 1. If I plug 2 into the I get 3. I plug 3 into the I get 5, and so on. So, my guess is that this is going to equal to n squared. So the sum of the first n positive odd numbers sums to n squared. Now, is this a true statement? I don't know. This is still a question mark. But I should mention that I want to prove this for all n, which is in z plus. So any positive integer is going to have this property. Now, again, is it true? We're gonna see whether or not this is true upcoming, but this is the way that we're going to set up the proof, and this is the very first step that we need to do whenever we tackle a problem, right? So, what is the statement that we are trying to prove, and what is the universe that we're trying to prove it on? The universe sometimes is even more important than the actual statement. Now, notice I just want you to see the statement here. You can somehow say that this statement is an open statement. It's an open proposition because it involves a variable n, and we don't know what n is. We know that there is a universe governing n, but what exactly is n? And so this is an open statement. Well, we can say that this must be true for all n, and this statement must be true. But nonetheless, we have this. We'll call it p of n as an open statement. Now, again, I just want you to remind you that an open statement means that as soon as I know what n is, I have a value that is true or false. It can be evaluated to true or false. Okay, so it's not a function. P of n is not a function. It is a true or false statement. Okay, all right. So that is kind of the motivation for this topic. Now, I'm going to kind of go on the aside a little bit here and talk about a principle called well ordering principle. It turns out that this principle is actually very important to mathematical induction. And if we don't use it, if we don't have the well ordering principle, mathematical induction is actually useless. So let me first of all give the introduction to this. Given a set of integers, the well ordering principle is always true. That's a very straightforward statement. And the well ordering principle goes like this: every non empty set of non negative integers has a least element. Now, there's a lot of nons here, but I just want to point out exactly what this theorem is trying to say. So if I have non-negative integers, now non-negative integers, remember, is the set n, right? That starts with 0, 1, 2, and so on. If I take any non-empty set of this, like a subset of this, guaranteed, I will be able to have a least element. Okay, so if I just take the set n, the least element is 0, right? So if I take, let's say, z plus is a subset of n, then the smallest element of z plus is 1. In fact, any subset that I take of the non-negative integers is going to be guaranteed to have a smallest integer. Now, before you say, well, isn't that always true? Isn't that true of every non-negative set? Well, no, not exactly. Because if I say, what is the smallest element in Z plus? Well, yeah, you can say that the smallest element is 1, right? But if I gave you another set, let's say I gave you something like the rational numbers, Q plus, what is the smallest positive rational number, right? Now, you can say 1, but there's actually a smaller rational number than that. It's 1/2, or 1/5, or 1/10, 1/100th, 1/1000th. So you can get very close to 0. Now, 0, remember, is not a positive number, right? So you can get very close to 0, but it will never get there, right? So what is the smallest? There is no smallest for the positive rational numbers. And the same argument goes for real numbers. What is the smallest positive real number? There isn't one, right? So you can have 0.1, 0.001, 0.000001. You can go on forever, right? So there is no smallest positive real number. So there's something special about the positive integers, right? So let's take a look at what that is. Now, again, the well ordering principle says if I have a subset of non negative integers, then for sure it must have a least element. Okay, so this theorem actually is quite useful in proving what you see on the left hand side here. So let's try to prove that given a and d. So if I give you the numbers a, which is an integer, and d, which is a positive integer, there are unique integers q and r, which falls between 0 and d, such that a is equal to dq plus r. Now, if this looks familiar, we've seen this already, right? We've seen this. This was called our division algorithm. So what we're going to do is actually prove 1/2 of this, one part of this. There is this word called unique. Now, unique is a word that you're going to see many times in the rest of the course. And in a second, I'm going to define exactly what unique means. What does it mean to say that something is unique? But for now, what I want to prove is that this element exists. Okay, so the Q and R exists. So let's say I give you A and D. So you're given the values A and D. So given A and D. Okay, and they are constrained as what is stated here. So I'm going to make a set S, which is x such that x is equal to a minus dq. Now, notice that I've just moved dq to the other side of this equation, and it has the form of r. Okay, so x has the form of r. So I'm going to take in this set everything that fits the equation that will give us r, and I'm going to assign x as a non-negative integer. Okay, so x is a non-negative integer, and then q is an integer. All right, so now just imagine you are given a and d, you know what they are constants. Can we always assign a q so that x is a positive or non-negative integer? Okay, so let me say that one more time. Let's say I already know what a and d are. They are fixed. Is it true that I can always find at least one q, which is an integer, that will make x a non-negative integer? And I hope you can see that yes, it's clear that you can always find a q, because the q can be a positive number, it can be a negative number, it could be anything, right? So I can always find a number so that x is non-negative. Okay, so the next step I'm going to take here is that I can conclude that S is not empty. It cannot be empty, right? Because Q is any integer. Okay, because Q can be positive or negative. Okay, and that is why S cannot be an empty statement or an empty set. Okay, so what do we have? S is a non-empty set of non-negative integers, right? So what did we just say about every non-empty set of non-negative integers? It must have a least element. So the next step is by the well-ordering principle. Okay, I'm just going to call it WOP. By the well-ordering principle, S has a smallest element. We'll call it R. Okay, so therefore, we can say Q and R must exist. Okay. Now, what does must exist mean? Well, another way to say must exist is that there's at least one of them. All right. So now we can take a little bit of a sidetrack. Okay. So I'm going to define right now what uniqueness means. And over the next few weeks, we are going to be using this idea of uniqueness many, many times. So let's work out a way that we can define uniqueness. So let me go to a white screen here. Now, this is definitely an aside. I'm going back to knowledge that we talked about in topic three when we talked about quantified logic. All right. So there is a logic. There is a quantifier that is an existence, right? So when we write something like this is read as there's at least one x, so that p of x is true. Okay, so there is at least one x, so that p of x is true. Now, what if you wanted to say that this x is unique to p of x? There's only one x that makes p of x true. Okay, so there's actually a symbol for this, which we don't usually use because it's not something that's supported very well in like computer languages or something like that. But the way that we would write uniqueness is we would write an exclamation mark. Okay, now instead, this is read as there's a unique x such that p of x. Now, what does unique mean? It means one and only one. Okay, so not zero, not two, one and only one. So, for example, if my p of x was the statement x squared equals x, okay, and let's say x is in the universe of integers. All right, so if you take a look at the left-hand side statement, right, this says there's at least one x so that p of x is true. And this is a true statement, right? So there's at least one x such that p of x is true because 0 and 1 both work under this formula. But is it unique? No, it's not. So this would be a false statement. Okay, so if p of x was x squared equals x, then this would be a false statement because it is not a unique x that fits this p of x. Now, remember I said earlier that the uniqueness symbol is actually not used that often. And the reason is because we can actually represent the uniqueness symbol using just the symbols, the quantifiers that we've seen before. For example, we can use the for all quantifier, and then we can use the existence quantifier to mimic the logic of uniqueness. Okay, so this is how we're going to do this. If we want to translate there's a unique x such that p of x, there's a unique x such that p of x, I'm going to have two parts. Okay, so the first part for uniqueness. Now this is very important. So please take note of this. You can watch this part again, but just know that this part is very important for the next few lectures. So the first part of uniqueness is that it must exist. Okay, so the first thing is there has to be at least one. Okay, so here's the first part. There's at least one x such that p of x is true. Okay, there's at least one, and at least one means greater than or equal to one. Okay, that's the first part of the logic. The second part of the logic is that there's at most one x such that p of x. Now, at most one is a little bit harder to write, but let's see if we can reason this out. So I want to write at most one. So at most one is going to be a for all, x1 and x2. Now I'm going to imagine that there's an x1 and an x2 that makes p of x true. Okay, I'll say that again. If x1 and x2 both make p of x1, make p of x true, then what should we conclude? Well, we can maybe say if this is at most one, then these two x1s and x2s cannot exist simultaneously. Or another way we can say this is that x1 and x2 must be equal. Okay, so here's my logic. P of x1 and P of x2, if they're both true, then x1 must equal x2. This is an equality that has to be true. Okay, so what this is saying, what this logic is telling us, is that there's at most one, which is less than or equal to one, which is essentially zero or one. Okay, now this statement is true and it must guarantee that there's only one, there's at most one that makes P of x true. So again, here's the logic. If I take a look at any two x's in the universe, if P of x1 is true and P of x2 is true, then that means they must be the same. Okay, guarantees that they are the same. So this is the logic behind at most one. Now, some of you might be looking at this and saying, wait a minute, why is this at most one and not one? Right? Why is this not the sole definition for uniqueness? And the reason is, let's imagine that there's no x. There's no x in the universe that makes P of x true. Okay, there's zero x that makes P of x true. This is still a true statement. Why? Because this will always be false. Okay, so again, imagine a case where there's no x's that makes P of x true, right? That would mean that the premise is always false. And what did we say? When the premise is always false, the whole statement is true, right? So false implies anything is always true. So I hope you can see that at most one, meaning zero or one, is represented by this logic. Okay, so finally, how do we write uniqueness? We write one and two. So the statement one and the statement two together is going to state that there is a unique x so that P of x is true. There's one and only one, right? It's greater than one, greater than or equal to one, and less than or equal to one. So therefore, it must be equal to one. Okay, so I hope you got that side note. And I did take a kind of a 90-degree turn there. But the reason that I wanted to talk about this is because in order to prove uniqueness, we have to prove those two parts. We have to prove at least one, and we have to prove at most one. So my question now is, take a look at this proof again. What did we just prove about uniqueness? Well, the answer is, I proved that there's at least one. So I only proved part one of this, right? So I only proved part one. Part two, I have to still prove, and you can definitely do this in your own time. I think we have all the mathematical things that we need in order to make this proof. But the idea is that Q and R is unique to A and D. So what we need to do is, let's imagine there's two pairs of Q and R. And what we need to show is that those two pairs must be the same. Okay, they have to be the same pair of Q and R. And this is a proof that I'm not going to do at this point. Maybe if there's time in later on in the course, I might do this proof. But just know that if we were really to prove uniqueness for this question, I've only proven one half of it. Okay, so this is only first part of the proof. The second part of the proof is missing. Okay, so all of this to say that there is a mathematical induction proof that we're going to talk about in this section that relies very heavily on the well ordering principle. So what mathematical induction is it's a technique that proves theorem of the form for all n p of n or for all x p of x in the universe of positive numbers, but any subset, basically any subset that has a smallest object and has some kind of pattern going forward. So, so first, we know from the well ordering principle that it has a set, it has a smallest value. So this set has the smallest value. So there's going to be a basis step. So I need to make sure that whatever statement that I'm trying to prove, that the p of the smallest element must be true. And that is called the basis step. Okay, that's called the basis step. There's also an induction step, which says if I have p of k, then p of k plus 1 must be true as well. Okay, for every k, if p of k is true, then p of k plus 1 is true as well. All right, so here's our definition of mathematical induction. Okay, so first, I need to show P of 1 is true. Then I need to show that for all k, P of k implies P of k plus 1. Now, there's the implies, which is great because we know how to prove the form of something implies something. Okay, so this is good. We've turned it into a form that we know how to prove. And if we're able to prove those two things, then the conclusion is that for all n, P of n is true. Okay, now let's first talk about why. Okay, now I'm going to explain why. This is a very high level explanation of why mathematical induction works. But if this doesn't make sense to you at the end of this explanation, what I want you to do is take a look at all the proofs that we're going to do with mathematical induction and come back and see if you see if this explanation makes sense. Okay. All right. So let's say that I am able to show that P of 1 and P of k implies P of k plus 1. So number 1 is true. Number 2 is also true. Now, in particular, if number 2 is true, then number 3 is also true, which is P of 1 implies P of 2. Why do we know that this is true? Well, because every k is like that, right? So every k implies k plus 1. So in particular, P of 1 implies P of 2. Okay, therefore, what can we say? P of 2 must be true, right? So 1 implies 2. We have 1, so therefore 2 is true, right? So this is from modus ponens. This is a modus ponens law. Now, I think everyone knows where I'm going with this. Number 5, I can say P of 2 implies P of 3 because number 2 was true. And therefore, I can say P of 3 is true, right? From number 4 and number 5, I can say that P of 3 is true, again, from modus ponens law. So I hope you can see that this is going to go on forever, right? So if we are able to prove number 1 and number 2, we're basically done, right? Everything else must be true. Now, what did I say earlier about the well ordering principle? The well ordering principle guarantees that in my universe, there must be a smallest element, right? So if there is no smallest element, or for that matter, if P of 1 cannot be shown, right? So if I don't know that P of 1 is true, can we make the rest of the argument? The answer is no. All we have is a bunch of implies and nothing is true. Okay? So so that's why P of 1, the basis step, is actually very important to our proof. Okay. Now here in our definition, we did write P of n0 being the smallest number in the universe, just because sometimes the universe is not z plus. Sometimes the universe could be n. It could be somewhere, greater than 20, right? So all the numbers greater than 20. So that is going to be the starting point for our induction. All right, so that is the definition um, of mathematical induction. So let's do a very quick proof just to see how the concept goes, and then we'll move on to other types of proofs that mathematical induction helps us to do as well. All right, so all right, just move the words out of the way there. So again, the mathematical induction proofs consists of the basis step as well as the inductive step. Now, there's generally 3 steps to mathematical induction. The first step is actually not shown here. The first step is actually coming up with the open statement. Now, oftentimes, I will tell you what the open statement is directly in the question, like what you're seeing here on the left-hand side. But other times, you have to put together the P of n yourself, right? You have to put together the open statement yourself. So here, this is pretty obvious. My P of n is the statement. So this is my P of n. The statement that the sum of I equals 1 up to n of I is equal to n times n plus 1 divided by 2. That is the statement that I want to prove. And I want to prove this for all n, which is which is in z plus. Okay, so the universe is z plus. So we know there's a smallest object, 1. So this is our first step. Our second step is to show that there is that the smallest object is true. Okay, so the next thing we're going to do is plug in the smallest object. So is P of 1 true? Now, this is part of my proof, right? So I have to somehow show definitively that P of 1 is a true statement. So I'm going to plug the 1 directly into the n, and I'm going to get that the summation from 1 up to 1 of I is equal to 1 plus 1 divided by 2. So now we have that uh, the summation from 1 up to 1 is equal to 1. So this should be a true statement. Now, this is very important. I want to remind you once again that the P of n is a true or false statement. It is not a function. Okay, so please don't get that wrong, because a lot of people are going to get this wrong on the quiz. You're going to write down that P of 1 equals 1, and that's not a true statement, right? So P of 1 is not a function. It is a true or false statement. So you have to write down what is the statement, right? What is the true or false statement? Okay, so P of 1 is true. And now I'm going to move on to the third step. So the second step was our basis. And now the third step is our induction, is our inductive step. So this is where I want to show that for all k, P of k implies P of k plus 1. Now I know I used n here, but just understand it's just some variable. So I want to show that P of k implies P of k plus 1 is true for every k in the in the universe. Okay, so the way that I'm going to do this is that I want to show P of k implies P of k plus 1. So as always, we're going to assume the premise and show the conclusion. Okay, so I'm going to assume that P of k is true. Now, what is P of k? It is the summation. So I'm just going to write assume here. Assume that the summation from 1 up to k of I is equal to k plus 1 divided by 2. Now, this is something that we know to be true. Okay, this is part of the premise. Remember from the very beginning when we did the induction proofs, we can just look at this statement as being true, and we can use it to prove other statements as well. Okay, so the next thing we want to do is derive the statement P of k plus 1. So in my mind, I need to think about what is the statement P of k plus 1. In fact, I'm going to write a different color here. I'm just going to write this on the side. As you do this more and more, you're going to be able to visualize what P of k plus 1 is, but I'm just going to write it down for now. So P of k plus 1 is the statement that the sum from 1 up to k plus 1 of I is equal to k plus 1 times k plus 1, which is k plus 2, divided by 2. So ultimately, if this was a true statement, what I want to do is show that P of k plus 1 must also be true. Okay, so how do we do that? Well, for a summation, we typically start with one side of this equality. So we start with the sum from 1 up to k plus 1 of I. Okay, so we start with this left-hand side. Okay, now just take a second to visualize what this summation is. When I sum the I from 1 up to k, this is essentially equal to 1 plus 2 plus 3 all the way up to k, right? And what is this? Well, if we sum up to k plus 1, this is 1 plus 2 plus all the way up to k plus k plus 1. So the first thing we have to realize is what is the difference between the left-hand side and between the two summations. So the real difference between the two summations is that those parts match, but the difference is k plus 1. It's that very last term. So do you agree if I write this following equation? The sum from 1 up to k plus 1 is equal to the sum from 1 up to k plus the last term, which is k plus 1. Okay, now I hope everyone is able to see what that is, but this is going to help us because the next step is that now I can substitute. So you see this part and this part are the same. So I'm just going to substitute because I already know that the sum up to k is equal to k times k plus 1 divided by 2. Right, so I'm just going to substitute that in because I already know that that's what it equals. And the last step is I have to use mathematics to show that the left-hand side, sorry, the right-hand side here is in fact equal to the equation that I have. Now, this part is quite simple because, at least in this case, it's quite simple because what we need to do is just do a common denominator of the two, right? Now we can factor out the k plus 1, and we'll get k plus 1 times k plus 2 divided by 2. And altogether, what we have is that the summation from 1 up to k plus 1 is equal to k plus 1 times k plus 2 divided by 2. And this is showing that p of k plus 1 must be implied. Okay, so we have that p of k is true, right? P of k is true. We use that fact. So notice that we did make a substitution. We use that fact to show that p of k plus 1 must also be true. All right, so just know that as we do more and more of these proofs, that um, that you will have to use p of k somewhere in your proof. If you're finding that you're able to prove the p of k plus 1, you're able to show that statement without going back and looking at p of k, then you're doing the proof wrong. It is not a mathematical induction proof, right? You may have proved it, but it's not a mathematical induction proof. So mathematical induction proof always require us to go back to p of k to see if to use that fact in order to show that p of k plus 1 must also be true. Okay, so I hope you're able to start to see where this mathematical induction problem comes from. But once again, I just want to go over the main idea. Whenever you're given a proof in mathematical induction, the very first step is to come up with your P of n. The P of n is a true or false statement. The second step is to show the basis, which means look at the smallest element that can be plugged into n, and is it true? If you find it not to be true, then you're done. The statement is already false, right? You've already found a counterexample to it. The third step is the hardest one, which is the induction step. So induction step, we assume that P of k is true, and using that fact, using the P of k is true fact, show that P of k plus 1 must also be true. That's it. That's what we're going to do for every single proof. But you're going to realize is that mathematical induction can be used in all sorts of areas. So not only summations, but we can actually use it for a lot of different types of proofs. So when we come back in the next video, I'm going to show you other types of proofs that we can do with mathematical induction.